Hello and welcome to Toddcast number 60. So we're tying off the alcohol carbonyl oxidation reduction interaction, and I'm going to focus a lot more on this time some bioexamples and some things you just have to flat out memorize, different ways we carry out reactions. So this is a chapter where flashcards, as you start to finish it off, whatever, like however you're taking this class, whenever you're taking this class, quarter system, semester system, etc. This is a chapter, carbonyls, that is loaded with information, and this is where I just think flashcards start to be somewhat helpful, electronic or paper version. Okay, so oxidation of an alcohol into whatever compound it's going to turn into. And so want to just emphasize that there is some mechanistic I don't know, explanation for why we get the products we get. For a lot of these, though, the intermediates get a little more complex than we want for this level of class. So we'll say, oh, it just happens, but I do want to somewhat go into why it does. Okay, so first and foremost, these are color coordinated so we know where things end up. This blue one coming off a carbon. So this is going to become an H minus, a hydride, so it's going to end up somewhere on, I don't know, whatever is getting reduced. So if I use CrO3 in water, it actually becomes H2CrO4. This O is free to attack, and you're going to end up, in that case, transferring a proton to this OH and it leaves. So I now have the alcohol bound to the chromium, and water is a side product. Water is going to, I guess, just help facilitate transfer of charge. But I have this group, this alcohol now. So if we have this, take this off, these electrons can go to the O, and those electrons there can go back to the chromium. So again, not asking you to know this, but know that these electrons from that bond are going to ultimately go to oxygen. And so the chromium now is an HCO3 minus. So if I calculate the oxidation state, +1 for H, -6 for the three carbon or three oxygens. So +1 -6 is -5. Overall, it's -1. So chromium has to go to +4 on its way to eventually becoming +3. So it started out +6. It is now down to +4, which makes sense because the oxidation of an alcohol to a ketone involves the gain of a bond to O and loss of bond to H, so that's 2 electrons. So it will get reduced by 2 electrons, or oxidized, excuse me, by 2 electrons, causing chromium. That's it. As referring to, that chromium will be reduced from +6 to +4, and eventually gets reduced one more time to +3. And so that's a little more above the pay grade of what we're going to deal with. But just note that you lose an H from the carbon. Okay. Oxidation of alcohols to carbonyls, take two. This is just flat out memorizing the way things work and how many reagents we deal with. So sodium dichromate, very similar to CrO4 2 minus, CrO3, just different conditions that we have them in. But in acidic conditions, chromate will oxidize a primary alcohol all the way up to a carboxylic acid. It can only be stopped at the aldehyde if we add a poison. That poison is pyridine. And what happens is the pyridine actually complexes, it binds to the chromium, so that lone pair on the pyridine will be donated to chromium and hold it in place. And when it does that, two things happen. Number one, it doesn't allow for the chromium to interact in the way it wants to with the species being oxidized. And number two, it allows us to do the reaction in the absence of water. You have to put water in there because you actually have to turn, and we'll haven't turned done it yet, but if you have two OHs on a carbon, it is known as a diol. And specifically, it's a geminal diol because they're both coming on the same carbon. If you don't have water, you can't convert the carbonyl to a geminal so it can't get oxidized any further than just one H. So we lose one of these H's to get the aldehyde. We use PCC. One of the P stands for pyridine, so it's pyridine chlorochromate. I guess there's only one P, it stands for pyridine. So pyridine is the poison that stops this reaction. Okay, so this concoction, PCC, is HCl, chromate, and pyridine, and you end up getting a chromate chloride that's been protonated. Okay. Next reaction, the Dies-Martin, and well, just a very weird, complicated bi-ring system that has a whole bunch of O acetates attached. And for whatever reason, it complexes with the alcohol and again prevents it from, once it forms a ketone, from going any further, or once it forms the aldehyde from keeping from going any further. So chromate, PCC, KMNO4 can do it under cold conditions. The Dies-Martin reaction, and then note that it can be a primary alcohol going to aldehyde or a secondary alcohol going to a ketone, as mentioned. And then something called Swern oxidation. So Swern, Dies-Martin, that's two words. Not going to ask you to memorize names necessarily, but I am going to use names because if you hang out with O chemists, you're supposed to know the name, so you can talk about things, you just know what it is. DMSO is a solvent. COCl2 is your intermediate reactant. The O can attack this carbon, kick out a Cl, and then it's, I don't know, in a perfect position to start gaining and or losing electrons, depending on which species you're talking about. But it basically sets you up to carry out the oxidation. The key thing I just want you to know is that it can oxidize the same things that PCC and DMP can, and KMNO4 can oxidize. So this is just unadulterated memorization. Um, Biological systems. This is where I think it gets kind of interesting. Um, but there's a molecule known as NADH, and this R represents a very significant amount of the rest of the molecule. So just not going to pay attention too much to what that is, but just say when nitrogen kicks in, you can send that H to a carbonyl. So NADH can give up that H right there, that H minus, that reductive H is going to attack a carbonyl. The lone pair on oxygen has that bond break. So I should have one more thing, and that is that bond going to that O, and then the lone pair on that O going pick up an H off a base. So you end up with NAD plus. So that H is now gone, now forms the aromatic ring. And the H has been out of here, and you picked up an H on the O. So it picked up this, an acidic proton, and it generated the conjugate base. Okay, so far so good. So biological cases, we have NADH and NAD plus. So going in just the reverse direction, NADH going to NAD plus does one thing, NAD plus going to NADH, just the opposite. A base comes in, plucks off that H, those electrons go in, pushing that H to that point, it moves back over. So it's pretty much just NAD plus going to NADH. It's getting reduced, so the other compound must be getting oxidized. Hence, we're going from an alcohol to a ketone. But it goes the other way as well. NADH rich in H, so it's a reducing agent. It itself will get oxidized, but it'll transfer an H. You get a new carbon-hydrogen bond, which is reductive in nature. So hopefully this seems okay. Knowing what NADH and NAD plus are will help in your bio studies. Okay, so if I want to take this compound right here, note that you can reduce or oxidize the two carbonyls into OHs on a benzene ring. This is a very, very common bio reduction or oxidation, depending on which direction we go. So quinone and hydroxyquinone, just common molecules. So just want to toss it in there because common in bio, common in bio. So I want to consider two processes. I don't know, depending on where you go to school, you may or may not have seen this at this point, but I've taught at a couple different universities, two community colleges and over the years, and most every school been affiliated with has physiology, cell bio, molecular biology, some of the really intense bio classes are taught in the sophomore or junior year. And so you've seen OChem beforehand. So if you're taking OChem right now and you go to a school with a traditional curriculum, you may not have dealt with glycolysis. I apologize for that. But for whatever reason, there are some schools out there that make first year students, their first semester at college, take cell biology, one of the most intense bio classes you'll take. And the problem in doing this is that you end up learning a lot of bio by pure memorization as opposed to understanding the chemistry behind it. And so going back and studying this in biochem will help. Um, and so again, I'm assuming nobody's taking biochem. So a few people watching this have taken cell bio. Um, and hopefully you've been exposed to glycolysis. But glycolysis converts glucose to pyruvate. And so glucose is 6 carbons long, pyruvate is 3 carbons, so you get 2 pyruvates. So if you break something down, just point of interest, we reductively build up and we oxidatively break down. So if you think about something like anabolic steroids cause reduction, so they build the person up, they bulk up. It's not exactly the same thing, but it's a good visual. So just breakdown is oxidative, buildup is reductive. So glycolysis is going from a C6 species to two C3 species. So it's a breakdown, so it's oxidative. So we need to add an oxidizing agent, something poor in H. Although they don't emphasize this in bio because I'm an O chemist, I pay attention to reagents. When it's a carbonyl, we typically use NAD plus, maybe NADPH plus, or NADP plus going to NADPH. But for carbonyls, we typically use NAD plus or NADH. For alkene chemistry, we usually use FADH2 or FAD. But for now, we'll just go with this. So glycolysis involves glucose. So here's my glucose. It's actually an alpha glucose. If you happen to know, carbon 6 when it's up and carbon or hydroxyl 1 when it's down, when they're trans. It is an alpha. So this is alpha D-glucopyranose. It has to be alpha for the enzyme to transport it into the cell to bind it. And so it ends up that we selectively deal with the alpha enantiomer or diastereomer, depending on what I'm comparing to. Okay, ATP is going to go in, ADP is going to come out. So I'm investing that energy. But in the end, I'm going to end up getting 4 ATP. So 2 go in, 4 come out. The reason it is 2 is it's 1 for each of the pyruvates. So in it with 2 pyruvates, so let's just count bonds to O and see how we did. 1, 2, 3, 4, 5, 6, 7 C to O bonds. In the end, we have 1, 2, 3, 4, 5 times 2, so 10 carbon oxygen bonds. It is increased by 3 CO bonds, so it's gained oxygen. It is oxidation. Because it is getting oxidized, we couple it with a reduction. So NAD plus going to NADH is a reductive process. So far, so good. PI, inorganic phosphate, is what's going to bind ADP to convert it to ATP. Okay, hopefully that seems fine. One more process. So that was an oxidative process. Fatty acid synthesis, a buildup, you're building a molecule, so it's reductive in nature. So this is going to just, again, be a big picture scenario, but buildup is reductive, metabolic processes, or anabolic processes, excuse me, build things up. So that means it is getting reduced, so it requires a reducing agent, something rich in H. So the reactant that you're coupling it with. So this is reactions going on here, one of the steps. and I'm going to couple it. So my first thought, it's a carbonyl, so it's got to be an add. It's got to be rich in H because it is getting, this compound is getting oxidized. So reducing agents get oxidized. So perfect. NADH, again, want to emphasize that this H, let's say make it blue, is going to be the one that goes on here as a blue H. H plus, I'll make it red. It is the one that protonates the O to help facilitate this. Just random point of interest, but it's actually not NADH, it's NADPH for this one. So I kind of lied, but I don't know my bio well enough to know when I'm lying, but it's very similar. The reaction is essentially the same thing. That ties off this group of information. We will continue with carbonyl reactions in future podcasts, but we're making happy high trails. Only, I believe, 6 more to go. So thank you for joining in, and I will stop the recording and see you the next podcast. Bye.